Welcome to the fifth lecture on mass transfer operation 1. We are discussing diffusion mass transfer. Before going through this discussion, let us have recap on our previous lecture. We have considered steady state molecular diffusion in fluids under stagnant and laminar flow conditions. Under this, the first case we have considered steady state molecular diffusion through a constant area. Under constant area, we have considered the first case is steady state diffusion through non-diffusing B, steady state equimolar counter diffusion, and the third case we have considered non-equimolar counter diffusion. In this lecture, we will consider steady state diffusion through a variable area. The left hand side of this figure shows the schematic of diffusion of A through a uniformly tapered geometry. So, as you can see, the area on the right hand side of the figure of a triangle which side is A2 to which is tapered towards the left side of this figure, which is the triangular shape face, which is area of A1. Obviously, A1 is at point 1 and A2 is at point 2 and A1 is less than A2. So, consider a component A is diffusing at steady state through a equimolar triangle conduit which is tapered uniformly. Let us consider A is diffusing through stagnant non-diffusing B component. Now, for an equilateral triangle, the formula for area where A is the length of one side can be written as A is equal to half into side into altitude. The altitude of triangle, equilateral triangle, is root 3 by 2 into A. A is the side of the triangle. Now, the area A would be half into side is A into the altitude which is root 3 by 2 A, which is equal to root 3 by 4 A square. So, now returning to the Fick's law formula, at position x of A through a triangle of stagnant B can be written as Na into 1 minus Pa by Pt is equal to minus dAb by RT dPa dx. Na is the flux, molar flux, and Pa is the partial pressure of a component A, Pt is the total pressure, dAb is the binary diffusion coefficient of component A into the non-diffusing B, R is the universal gas constant, T is the temperature, and dPa by dx is the partial pressure gradient with respect to x. Now, if we define Na is equal to Na cap divided by A, where Na cap is the molar flow rate, which would be equal to, if we equal to 4 by root 3 Na cap by A square, if we substitute the area in these equations as we have calculated before. So, Na, as we said, Na is the rate of diffusion of A in kilomole per second. So, the above equations can be written as minus R T by d A B into 4 n A cap by root over 3 A square d x, which would be equal to P T into d P A by P T minus P A. Now, before limits are imposed, it must be remembered that A is a function of x. That means, A is varying with respect to the distance x. As the size of the triangle uniformly tapered with distance along the duct. So, we need to have a relations between A and x. Now, A would be equal to A1, which is at point 1 in this figure, plus A2 minus A1 divided by x2 minus x1 into x minus x1. So, this is the relation between the A and the distance. If we just simplify, it would be equal to A1 plus A2 minus A1 by x2 minus x1 into x minus A2 minus A1 divided by x2 minus x1 into x1. So, if we just differentiate with respect to x this equation, then it would be dA by dx would be equal to 0 plus A2 minus A1 by x2 minus x1 into 1 minus A2 minus A1 divided by x2 minus x1 into 0. So, which will be simplified to A2 minus A1 by x2 minus x1. Therefore, dx would be equal to x2 minus x1 divided by A2 minus A1 into dA. So, we have a relations between dx and dA. Now, if we substitute x for A and integrating with limits of partial pressure of component A at 1 at triangle of site A1 and partial pressure of component A at point 2, that is PA2, when the triangle is of site A2, we can write minus RT NA cap divided by DAB into x2 minus x1 by A2 minus A1 integral A1 to A2 4 divided by root 3 A square dA, which would be equal to PT integral PA1 to PA2 dPA divided by PT minus PA. So, this we can simplify, we can integrate this and we will obtain minus 4 RT NA cap divided by root 3 DAB into x2 minus x1 divided by A2 minus A1 into minus 1 to minus 1 divided by A with a limit A1 to A2. So, this would be equal to minus ln PT minus PA with a limit PA1 to P2, and hence the left hand side can be written as 4 RT NA cap divided by root 3 DAB into x2 minus x1 divided by A2 minus A1 into 1 by A1 minus 1 by A2, if we put the limit in the earlier equation, which would be equal to ln PT minus PA2 divided by PT minus PA1. If we simplify this, it would be equal to NA cap A1 minus A2 divided by A1 into A2, which would be equal to root 3 DAB PT by 4 RT into A2 minus A1 divided by x2 minus x1 ln PT minus PA2 by PT minus PA1. So, now these equations we can just rearrange and simplify, from where we can write Na cap would be equal to root 3 dAB by 4 RT into PT into A1 into A2 divided by x2 minus x1 into ln PT minus PA2 by PT minus PA1. So, this is the final equations for steady state molecular diffusion through variable area. Now, let us consider one example. The carbon dioxide is diffusing through non-diffusing nitrogen at steady state in a conduit of 2 meter long at 300 Kelvin and a total pressure of 1 atmosphere. The partial pressure of carbon dioxide at the left end is 20 kilopascal and 5 kilopascal at the other end. The cross section of the conduit is in the shape of an equilateral triangle being 0.025 meter at the left and tapering uniformly to 0.05 meter at the right end. Now, we need to calculate the rate of transport of carbon dioxide. The diffusivity is given for dAB equal to 2 into 10 to the power minus 5 meter square per second. So, the value which are given diffusion coefficient which is equal to 2 into 10 to the power minus 5 meter square per second. R is known to us 8314 meter cube Pascal per kilomole Kelvin. T is the temperature which is given at 300 Kelvin. Total pressure PT is 1 atmosphere. So, it is 101.3 kilopascal which is equal to 1.013 into 10 to the power 5 Pascal. PA1 is equal to 20 kilopascal which is equal to 20 into 10 to the power 3 Pascal. PA2 is 5 kilopascal which is 5 into 10 to the power 3 Pascal. A1 is equal to 0.025 meter, A2 is equal to 0.05 meter, x2 minus x1 is 2 meter, the distance between the two end. Now, substituting the values given in the following equations, Na bar would be equal to root 3 dAB PT divided by 4 RT into A1 A2 into A1 into A2 divided by x2 minus x1 into ln PT minus PA2 divided by PT minus PA1. So, this Na cap is equal to Na bar here. Now, if we substitute the values root 3 into 2 into 10 to the power minus 5 meter square per second for diffusion coefficient, total pressure multiplied by the total pressure 101.3 into 10 to the power 3 Pascal into the A1, the length of site at point 1 of the triangle which is 0.025 meter, and then A2 which is the side of the triangle at point 2, that is 0.05 meter, divided by 4 into R 8314 meter cube Pascal by K mole into Kelvin into temperature is 300 Kelvin, the distance x2 minus x1 is 2 meter into ln PT is given 101.3 into 10 to the power 3 Pascal minus PA2 is 5 into 10 to the power 3 Pascal divided by PT which is 101.3 into 10 to the power 3 Pascal minus 20 into 10 to the power 3 Pascal. So, if we just calculate, it would be equal to 3.74 into 10 to the power minus 11 kilomole per second. So, this is the molar flow rate which is given in the problem to calculate. Now, let us consider diffusion from a sphere, where the area will vary. Examples of diffusion through the spherical shape bodies, one of them is the evaporation of a drop of liquid. So, if we take a drop of liquid and just put on a plane surface, the liquid droplet will slowly evaporate and its diameter will reduce slowly, and hence the area for the diffusions will also vary. Another example is the evaporations of a ball of naphthalene. If we just keep spherical naphthalene ball onto the air, then it will diffuse and slowly its diameter will decrease, because the naphthalene will diffuse to the air. This is another example, and then the third example is the diffusion of nutrient to a sphere like microorganism in a liquid. So, let us consider a sphere whose center is O and the radius is r1, and then the area radius is varying with time, and the partial pressure at the bulk is Pa2 and at the surface of the sphere is Pa1. Assume a constant number of moles Na of A from a sphere whose area is equal to 4 pi r square through stagnant B. Now, if we consider fixed law of diffusion, the rate of diffusion can be expressed as Na into 1 minus Pa by P total. Pa is the partial pressure of component A, which is equal to minus dAB by RT into dPA dr, where Na is equal to Na bar by 4 pi r square. So, we can just substitute this Na is equal to Na bar 4 pi r square. The equation 1 would be equal to minus RT Na bar divided by 4 pi dAB into dr by r square, which would be equal to P total into dPA by P total minus Pa. Now, integrating with limits of Pa2 at R2 and Pa1 at R1, it gives minus RT Na bar divided by 4 pi dAB P total into 1 by R1 minus 1 by R2 is equal to ln Pt or P total minus Pa2 divided by P total minus Pa1. Now, as R1 is very less than R2, which is at far away, then 1 by R2 would be approximately equal to 0. So, then the above equation 4 would be reduced to Na bar by 4 pi R1 square into dAB. The above equations would be reduced to Na bar divided by 4 pi R1 square equal to dAB P total into Pa1 minus Pa2 divided by RT PBLM R1, which would be equal to Na1, that is the flux at the surface. PBLM is the log mean partial pressure difference, as we have discussed before. Now, these equations can be simplified if PA1 is small compared to P, that is total pressure PT, since a dilute gas phase, then PBLM would be approximately equal to P total. Now, also if we set 2R1 is equal to D1, that is diameter, and then CA1 would be equal to PA1 by RT, the above equation, these equations, the PBLM and P total will cancelled out, and PA1 by RT would be CA1, which is the concentration at point 1 of component A, and PA2 by R2 would be equal to CA2, that is at concentration of component A at point 2. So, the above equations will reduce to Na1 would be equal to twice dAB by D1 into CA1 minus CA2. Now, let us consider one example. A sphere of naphthalene having a radius of 5 millimeter is suspended in a large volume of steel air at 310 Kelvin and 1 atmospheric pressure. The partial pressure at the surface of naphthalene at 310 Kelvin is 50 Pascal. Assume dilute gas phase. The diffusion coefficient of component A, that is DAB of naphthalene in air is at 310 Kelvin is given as 6 into 10 to the power minus 6 meter square per second. Now, we need to calculate the rate of evaporation of naphthalene from the surface. So, what are the parameters given? Let us note them down. DAB, the diffusion coefficient of naphthalene into air is component B, which is equal to 6 into 10 to the power minus 6 meter square per second. Partial pressure of component A at point 1 is 50 Pascal, and at PA2 is equal to 0 because it is dilute gas phase. R1 is equal to 5 by 1000 meter, since it is 5 millimeter. Capital R, which is universal gas constant, is known to us 8314 meter cube Pascal divided by kilomole Kelvin. PBLM, since it is dilute gas, PBLM would be equal to the total pressure PT, which is equal to 1 atmosphere. We can write this is 101.3 kilopascal, which is equal to 1.013 into 10 to the power 5 Pascal. Now, these are the parameters known to us, and this is the relations of the flux at the surface. We know for the spherical surface, Na cap or Na bar divided by 4 pi r r1 square is equal to dAB P total PA1 minus PA2 divided by RT PBM R1. Here PBM is PBLM, the log mean partial pressure difference, which is equal to Na1, the flux at the surface. So, if you substitute the values which are given over there, it would be 6 into 10 to the power minus 6 into 1.013 into 10 to the power 5 into 50 divided by 8314 into 310 into 1.013 into 10 to the power 5 into 0.05. So, this would be equal to 303.9 into 10 to the power minus 6 divided by 1305 54.22, which is equal to 0.023 into 10 to the power minus 6 kilomole per meter square second. So, this is the flux for the ball at the naphthalene at the surface. Now, let us consider steady state equimolar counter diffusion. So, this is a cylindrical geometry uniformly tapered. So, component A is diffusing at steady state through a circular conduit at point 1, the radius is r 1 and at point 2 it is r 2. So, we know that N A is equal to minus C into d A B d y A d x plus y A n. Now, it would be minus d A B by r t into p t d y A d x plus y A n. At position x in the conduit, A is diffusing through B by equimolar counter diffusion. Now, for equimolar counter diffusion, we know that N A would be equal to minus N B. So, the total molar flux N would be equal to N A plus N B, which would be equal to 0. At position x, the flux can be written as N A would be equal to minus d A B by r t into p t into d p a by p t divided by d x is equal to minus d A B by r t into d p a d x. Now, from this we can write N A would be equal to N A cap by pi r square, which is equal to minus d A B by r t into d p a d x. Now, using the geometry as shown, the variable radius r can be related to position x in the path as follows. R would be equal to r 2 minus r 1 divided by x 2 minus x 1 into x plus r 1. Now, if we substitute this value of r into over here, the above equations will lead to N A cap by pi integral x 1 to x 2 dx divided by r 2 minus r 1 by x 2 minus x 1 into x plus r 1 whole square, which would be equal to minus d A B by r t integral p a 1 to p a 2 into d p a. So, now let us consider C 1 is equal to r 2 minus r 1 divided by x 2 minus x 1. So, we can write the above equation as N A cap by pi integral x 1 to x 2 dx divided by C 1 x plus 1 whole square, which would be equal to minus d A B by r t integral p a 1 to p a 2 d p a. Let C 1 x plus r 1 is equal to z. So, if we just differentiate, then it would be dx would be equal to dz by C 1. Now, if we substitute the above equations, these equations would be N A cap by pi integral z 1 by z 2 dz by C 1 whole divided by z square would be equal to minus d A B by r t integral p a 1 to p a 2 d p a. So, if we integrate, it would be minus N A cap divided by pi C 1 into 1 by z with a limit z 1 to z 2, which would be equal to minus d A B by r t into p a with a limit p a 1 to p a 2. So, this would be written as N A cap by pi into C 1 whole into 1 by z 1 minus 1 by Z2, which is equal to dAB by RT into PA1 minus PA2. So, from there if we substitute Z1 and Z2, then it would be NA cap by pi C1 into 1 by C1 x1 plus R1 minus 1 by C1 x2 plus R1, which would be equal to dAB by RT PA1 minus PA2. So, now if we substitute CA1, it would be NA cap divided by pi R2 minus R1 divided by x2 minus x1 whole into 1 by R2 minus R1 divided by x2 minus x1 into x1 plus R1 minus 1 by R2 minus R1 divided by x2 minus x1 into x2 plus R1, which would be equal to dAB by RT PA1 minus PA2. So, finally, if we rearrange, the molar flow rate NA cap would be equal to dAB by RT into pi R2 minus R1 by x2 minus x1 into the partial pressure gradient PA1 minus PA2 whole divided by 1 by R2 minus R1 divided by x2 minus x1 into x2 plus R1 minus 1 by R2 minus R1 by x2 minus x1 into x1 plus R1. So, we obtained this relation. Now, after if we put x1 is equal to 0 and x2 is equal to L, and that means x2 minus x1 is L, the total distance from point 1 to point 2, the above equations we can write NA cap would be equal to dAB by RT into pi R2 minus R1 by L into PA1 minus PA2 divided by 1 by R2 minus 1 by R1, which would be equal to dAB by RT into pi R1 into R2 by L into the partial pressure gradient PA1 minus PA2. Now, let us consider one example. The carbon dioxide is diffusing at steady state through nitrogen by equimolar counter diffusion in a conduit of 2 meter length at 300 Kelvin and a total pressure of 1 atmosphere. The partial pressure of carbon dioxide at the left end is 20 kilopascal and 5 kilopascal at the other end. The cross section of the conduit is in the shape of cylindrical of radius 0.025 meter at the left end and tapering uniformly to a radius of 0.05 meter at the right end. We need to calculate the molar flow rate of carbon dioxide. The diffusivity of the component is dAB is equal to 2 into 10 to the power minus 5 meter square per second. Now, the data which are given can be noted. dAB is equal to 2 into 10 to the power minus 5 meter square per second. R is 8314 meter cube Pascal per kilomole Kelvin. T is the temperature, which is 300 Kelvin. Pt is the total pressure, which is at atmospheric pressure, which is equal to 101.3 kilopascal, which is equal to 1.013 into 10 to the power 5 Pascal. PA1 is 20 kilopascal, which is equal to 20 into 10 to the power 3 Pascal, and PA2 is 5 kilopascal, which is 5 into 10 to the power 3 Pascal. A1 is 0.025 meter and A2 is 0.05 meter. The distance between the two end or 2 point x1 and x2 point, which is L, is equal to x2 minus x1, which is 2 meter. Now, if we substitute the parameters which are given dAB, R, T, Pt and partial pressure of component A at 1 and partial pressure of component A at 2, and then the other values A1, A2 and the length. So, if we substitute these values in the following equation, we would obtain N A bar would be equal to this, which would be equal to 0.00785 into 15 divided by 4988400 into 10 to the power minus 2 kilomole per second, which is equal to N A bar is equal to 2.36 into 10 to the power minus 10 kilomole per second. Thank you very much for hearing this lecture.